Hey folks, welcome. Here we are going to take a look at section 3.4. It's the differential, and the only objective that we are going to focus on, that you could focus on when you look at the book, is objective 1, how we compute a differential. So here we go. This thing that's called the differential, what the differential does is it's used to study the relationship between changes in our independent variable and dependent variable values. So kind of think right there, the differential is used to study the relationship between changes in the x's and the f of x's, or y's, if you will. If you have a differentiable function of x, so if y is a differentiable function of x, we simply define the following. We're going to define the differential in x, and it's going to be noted with just simply a little dx. That's our independent variable. The differential in x dx is just simply the same thing as delta x. So dx, the differential in x, and delta x, a change in x. They're the exact same thing. Our differential in y, this is more exciting, this is more important, this is denoted dy. That's our dependent variable. The differential in y is given by dy equals f prime of x dx. I need you to know that. I need you to know dy equals f prime of x dx, where f prime of x is just the derivative of whatever the function is we're dealing with. So make a special note of that. Dy equals f prime of x dx. Now what I'm going to do here is I want to highlight some stuff. First off, I want to highlight the fact that delta y, we haven't talked about that yet, but it's just going to be the actual change in the dependent variable values. Dy is going to be an approximation of delta y. So take a look at the picture that's here. The blue curve, that's just the graph of some function. Don't know what the function is? I don't care. So if we're at this point on the blue curve and we go to this point here on the blue curve, we're gonna talk about the change in the y values and going from here to here on the blue curve. That's going to be the delta y. Well, if you're here at this point on the curve, and I'm just generically saying it has an x value of x, then you move to the right, delta x units, delta x. Well, that puts you over here at an x value of x plus delta x. For example, if x had a value of 3 and delta x had a value of 1, this x value here would be 3, this x value here would be 4. On the function, the blue curve on the function, this point would have an x coordinate of 3, this point here would have an x coordinate of 4. Well, the y coordinates, the y coordinate of this point is going to be f of x. The y coordinate of this point is going to be f of x plus delta x. So again, if x is 3, the y coordinate here would be f of 3. The y coordinate here would be f of 4 if x is 3 and delta x is 1. So how would you find the actual change in those y coordinates? See, that's the actual change in y coordinates on the function. Well, you would simply take this y coordinate and subtract that y coordinate. That's how you would get the actual change in y coordinates. That's delta y. The dy, now dy, by definition, let's go over it one more time, dy is f prime of x dx. Well, dy will give us an approximation of that actual change in y. Dy will give us an approximation of delta y. So let's look at what dy is. We have here dy is f prime of x dx. So again, it looks like this black line here, it's a tangent line. It looks like it's tangent to the curve, the blue curve. It looks like it's tangent right here at x. So how would I find the change in the y coordinates on the tangent line when I go from here to here? Well, if this has an x value of 3, it looks like to get the change in y values on the tangent line, That's dy. It looks like I would just simply do f prime of x, f prime of 3, times dx, whatever this dx is. So again, hopefully you can see that dy, you can think of dy as being change in y coordinates on a tangent line. But check it out, dy is pretty close. It's approximately equal to delta y. And I have a special bullet item here that if your dx, and remember dx is the same as delta x, if it's small, then it is a fact that dy will be approximately equal to delta y. And all this is going to be a setup for the next section that we do. When we do something called marginal analysis, we'll really look at some business functions. But for right now, it's I would like you to just remember this picture. Remember this picture. Remember dy is equal to f prime of x dx. Remember dy does a really good job of approximating delta y. And let's check out an example here, folks. First example, the function for the function f of x equals x cubed plus 8x plus 2. We're going to do two things here. We're going to evaluate delta y, that'd be the actual change in y coordinates, and we're going to determine dy for x equals 9 and delta x equals dx equals 0.1. So I think it's time that I head off to the chalkboard to do this. So why don't you, if you need to, write this example down, write it on a piece of paper, and all the particulars of it. And I'm going to head off to the chalkboard to do this example. Hey folks, the example we just left with was for the function f of x equals x cubed plus 8x plus 2. Evaluate delta y and dy for x equals 9, delta x equals dx equals 0.1. So the first thing I'm going to do here is I'm going to determine delta y. Remember, delta y is the actual change in y coordinates for the function itself. So here we go. To find delta y. First thing I'm going to notice is that we're starting at an x value of 9. So I'm going to make ordered pairs here. X is 9. Now to find the y value that would correspond to an x value of 9, this is just old algebra, you're going to take this 9, you're going to evaluate the function at 9. You have to find f of 9. You're going to take 9 and toss it in for the x's. And if you do that, you're going to get f of 9 is 803. So this 803 is f of 9. Okay, now the next x value I have is coming from the fact that my delta x is 0.1. So if I'm at an x value of 9 and delta x is 0.1, 9 plus 0.1 is 9.1. So that's the x coordinate of the next ordered pair. And how do I find the y coordinate? Well, that's right. I'm going to take 9.1 and toss it into the function that I'm given. I'm going to toss it in for x. So I'm going to find the f of 9.1. And when I crank this into my calculator, I get 828.371. So this tells me to get delta y, to get the change in the y coordinates, I want to know the change in these y coordinates. To get the change in the y coordinates, I just simply take 828.371 and I subtract 803. And boy, that gives me a 25.371. So delta y is 25.371. That's the actual change in y coordinates. Now to get dy, well, remember to get our definition we just solved for the differential in y, dy. Remember dy is f prime of x dx. So dy is, well, here's the function. Let's get the derivative of that function, f prime of x. So the derivative of this function is 3x squared plus 8. So there's dy. But now we want to determine dy when x is 9 and dx is 0.1. So all we have to do is take 9, toss it in here for the x, take 0.1 and toss it in for dx, and that gives us dy equals 3, times 9 squared plus 8 times 0.1. And when I crank that through my calculator, I get 25.1. So that's the value of dy, 25.1. And notice the value for dy is pretty darn close to the value of delta y. And that's something that we saw. Dy will be a good approximation for delta y as long as our delta x, which equals dx, is small. And 0.1, well, that is small. So hopefully that example makes sense. To make sure that you're really dialed into this material, I mean, we're not doing much in this section. So to make sure you're really dialed in, I would like you to pause the video and do number 23 in section 3.4. So go ahead, pause the video, do number 23, and after you've done 23, restart the video and we'll have a worked out solution for you. Alright folks, let's see if you got number 23 correct. In number 23, the function was x squared minus 2x minus 1. For x is 2, delta x equals dx equals 0.1. And here you were asked to find delta y and dy. So you know that I always, I tend to start by finding the delta y first. So we're at starting at an x value of 2 to get the y coordinate. Remember, find f of 2, toss 2 in here for the x's, and you should get f of 2, well, you should get it to be negative 1. And see the next x coordinate, well, we're starting at x is 2, delta x is 0.1, so 2 plus 0.1 is 2.1. To get the y coordinate, 2.1 comes in here for the x's, and you should have gotten negative 0.79. So that tells me delta y is the change in these y coordinates. It's a negative 0.79 minus a negative 1. So negative 0.79 minus negative 1. That's 0.21. That's what the change in the y coordinates would be. That's delta y. So here we go for dy. Well, the first thing I tend to do is I remember dy. We have to remember this, folks. We have to remember dy is equal to f prime of x dx. So dy equals, see the derivative of my function, f prime of x, that derivative is 2x minus 2. So there's my expression for dy. dy equals the quantity 2x minus 2 times dx. And now I just simply toss 2 in here for x and 0.1 in here for dx. So we get dy equals, well, 2 times a 2 minus a 2 times 0.1, and that gives us dy equals 0.2. And again, notice the dy equaling 0.2 is really close to the actual change in y, the delta y, which was 0.21. So hopefully you did 23, hopefully you got 0.21 for delta y, and you have 0.2 for dy. And that's it for number 23. So at this time, that's all there is for section 3-4. You should be able to do the homework now, and hopefully it all makes sense. Thanks for watching.